right. Thank you for coming. Thank you for inviting me. How many of you have heard about factor investing? So pretty much everybody. So as you know, factor investing is a very important part of the investment financial industry. Between $3 and $4 trillion are allocated to factor investing strategies. And those are strategies, those are vehicles that invest directly in factor investing. If we were to account for all the money that is invested indirectly in factor investing, it would be a multiple of that number. So it is by far the most popular investment approach. What if I were to tell you that this approach does not really have a solid scientific foundation? So I'll begin with the numbers. Can you show the slides? Good. Well, that's the performance of factor investing strategies going back to 2007. Why 2007? Well, it's when Goldman Sachs and Bloomberg began to track the performance of the most popular factors: value, momentum, quality, etc. And as you can see, it's a dismal performance. If you had invested in such fund, you would have made around 1% a year before transaction costs and management fees, with a very, very low Sharpe ratio, essentially doing nothing. So why is that? Remember, this is an investment approach that has been peer-reviewed to the infinity. There are literally thousands of papers published in the most high-ranking journals in finance supporting this. Why is it failing? Well, it is failing because it is based on very traditional statistical methods that were established back in the 1930s, what we might call the econometric canon. You buy a textbook at the bookshop, or you get it at the library. There are some very, very famous books of econometrics, and what you will find is approaches that are essentially associational. They have very little to do with what Professor Imbens presented this morning. And I celebrate, of course, that we have people of high intellect like Professor Imbens, who is changing the discipline. But the reality is that there is a battle for the soul of econometrics that is taking place today. Most financial econometricians are associational. Very, very few, Professor Imbens, one of them, is causal. And that's the difference. The difference is that these approaches just do not work. And remember, when we talk about $3–4 trillion invested in this, what we are talking is about pensions, savings. This is money that people actually need. This is not hedge fund money. This is money that many savers, retirees, are expecting to receive. They're expecting to get the return that was published in the journals, and that's not what they are getting. So what are we going to learn today? Every student of statistics learns that correlation does not imply causation. Association is an observational property. Professor Imbens made the case brilliantly this morning, so I'm very happy that he already got us started there. Causation is an interventional concept. It involves an experiment, whether real or simulated. Now, causality plays a crucial role in the scientific method. Why? Because scientific theories are statements of the form X causes Y through mechanism M. Whenever you think of a scientific theory, it always boils down to this kind of a statement. You do not find scientists saying, well, when this thing and this thing happens together. That's not really how science works. Imagine a doctor who says, well, you know, when you take this happens. No, a doctor needs to understand the mechanism. Without an understanding of the mechanism, you don't really have control over what that supposedly medication or treatment is doing. But that's not what factor investing does. What they do, what authors publish in papers in financial journals typically do is they identify a correlation. you can express it in different ways. They run some regressions, compute some p-values, and they establish an anomaly, what is called an anomaly. But there is never a causal theory explaining why this anomaly occurs. So essentially, they stop at the correlation, at the associational statement. These papers do not make, or very rarely make, a causal statement. As a result of that, there are hundreds of claim factors that have been published. I just mentioned 4 of the most popular, but the reality is that there are hundreds of them. That's what has been called the factor zoo. And what does it mean, this factor zoo? Well, what it means is that you find all sorts of claims that are based on very short time series that may or may not have worked for the past 20 years or so. And the paper is published, and people put money on those papers. I will explain how we can differentiate between 2 types of flaw claims, false claims. One is type A spuriosity. Those are statistical flukes. And number 2, type B spuriosity, that's non-causal association. Let's begin with causality in factor investing. Why do we care about causality? Well, we care about causality because to make a prediction is not enough. I will make a clear example later on. Even if we were able to forecast, let's say, some prices based on some observed phenomena, that would not be enough to fulfill our fiduciary duty towards investors. Factor investing models, in fact, have some appearance of causality. A researcher typically will choose a particular model specification of this form, some variable y that they want to predict, let's say, the average cross-sectional returns, as a function of some variable x that they believe is the cause of that outcome, let's say value, momentum, and then they add some other regressors that they want to control for. They may want to control for, let's say, the business cycle, the size of the company, the economic regime. And when you look at this function, clearly, it's a causal statement. That's the most puzzling part of this story. It is as if researchers initially want to make a causal claim, but they never deliver the goods. They never present the causal graph associated with this regression. Why do I say that? Well, because they are regressing y, supposedly in effect, as a function of some causes. They are not trying to regress x as a function of y. This is not a distributional statement. It's not a statement that you would obtain, for instance, through PCA. You would obtain through a distribution of bivariates. No, this is actually a causal statement. Another way of looking at this as a causal statement is that they choose a very specific method, multivariate linear regression models estimated through ordinary least squares. Now, as you know from Econometrics 101, ordinary least squares have some very interesting properties. For instance, they are non-orthogonal. They are non-orthogonal projections. So if we were to regress x as a function of y, we would not be able to obtain those coefficients based on the beta and gamma that we estimated here. There is a loss of information. Why? Because this is, in fact, a directional statement, x towards y. And as a result of that, there is some loss of information that would not occur, for instance, if you were to run an orthogonal regression. In addition, they also incorporate a number of causal assumptions when they run these regressors. For instance, they will apply y ordinary least squares because they have the property that they are linear estimators with minimum bias. They are the maximum likelihood estimators with minimum bias. In fact, the minimum variance among the unbiased. So that's the Gauss-Markov theorem. Well, that means that they are actually trying to estimate betas in an unbiased way. This means that they are willing to give a lot of forecasting power in order to obtain an unbiased estimator. You see? This is not a forecasting model. In a forecasting model, you are willing to take bias in exchange for for minimizing the sum of squares. Right? That's what you would do, for instance, if you run a random forest regression. A random forest regression, there is no claim of biasness. Why are they applying an estimator that is unbiased? Because this is, in fact, a causal statement. They are trying to estimate beta in an unbiased way. So the question is, if this is truly a causal model, where is the causal graph? How do they know what variables they need to control for? They never declare the confounders. They never declare the mediators. They never declare the colliders. So how do we know that this is the correct specification? We do not know. In fact, what has happened is that they choose the specification that maximizes the R square. Not that maximizes the probability of obtaining an unbiased estimator. Right? They are not trying to impose a specification that allows for an unbiased estimator. No, they are trying to maximize the R square. So the conclusion is that there is a causal denial. On one hand, they use econometric methods that come really from biology, given the work that from the 1930s of Ronald Fisher and Carl Pearson and Nyman and many others, biostatisticians. But then they hide essentially the causal statements. They introduce some causal assumptions, but then they hide the causal statements. This leads to a state of confusion where on one hand, the model has all the characteristics of causality, but then they make associational claims. They are never providing a causal graph that can be falsified, that can be validated. What are the implications? There are two implications to this. Number one, that because they run so many regressions without controlling for multiple testing, the probability of a false positive rate is no longer a 5%. This is something that we know since the 1930s. Bonferroni is a name that probably you have heard of. Very quickly after Pearson and Neyman produced their hypothesis testing procedure framework, Bonferroni was the first one within months of saying, well, but this is only possible if you run the test once. The moment that you run the test twice, this significant level is no longer 5%. Well, Pearson's response was, of course, well, who would run this twice? I mean, it's so hard to get these estimates. Well, today, of course, we run millions and billions of regressions. And very few people in financial econometrics are controlling for multiple testing. As a result of that, even if the true value of the Sharpe ratio is 0, because they only publish the best performing model out of thousands, even millions of regressions, the expected value of the Sharpe ratio is increasing with the number of trials, even if the true Sharpe ratio is 0. And that's what is reflective of the first slide that I show you. Right? In the papers that you find in the Journal of Finance, Review of Financial Studies, Journal of Financial Economics, etc., there are claims of Sharpe ratios of 1, 2, 3. But then what you obtain is 0. Why? Because the true Sharpe ratio was 0, but they chose the best model out of thousands that they run. So they may claim a Sharpe ratio of 2, but the real Sharpe ratio is going to be 0. So this is type 1, type A, spuriosity. And the solution to this is well known. You can either apply methods to correct for p-hacking, like Hochber published in 1988, or you can publish methods to control for backtest overfitting, like David Bailey and I published in the year 2014. Then you also have type B spuriosity. What is type B spuriosity? Suppose that the signal is real. There is, in fact, an association. That doesn't mean that it's a causal association. It could be a non-causal association. Again, Professor Imbens explained this morning how one may observe association when there is no effect at all, which would be type A, but there could be association that is biased, that maybe there is no arrow between X and Y, and yet we will observe an association. And this is because the association flows through a backdoor. And this is the key difference between association and causation. We all hear the statement, association does not imply causation, but why is that? Why is that? Because causation is a very special type of association. Causation is the association that flows through causal paths. In this case, there is no causal path between X and Y. And yet, we will observe association between X and Y because it goes through the backdoor path. Why does association flow through backdoor path? Because it does not care about the direction of the arrows. Association is not a statement about X causes Y. It's a statement about two things move together. And it doesn't matter what moves first. Observationally, they move together. This is what we need to do. We need to control, in this case, for this confounder set. Now, some econometricians have made the claim, well, then what you can do is you can just add some variables, some control variables in your regression, as many as you can think of. And if they are a confounder, great. You will be able to block this backdoor path. And if they are not, well, they are not harmful. Wrong. They're, of course, very harmful. As we all know, if you control for a collider, you will experience, again, a false association, because a collider blocks the backdoor path. However, when you control for it, it opens it. So the solution is not just to control for whatever you can think of. You have to control for confounders. You need to have a causal graph that discriminates between confounders, mediators, and colliders. Only with knowledge of the causal graph you can propose the correct specification. Let me give you a couple of examples. Type B1 spuriosity. That's the spuriosity that occurs when you under control. There is a confounder. Let's say in this case, you have a variable of the structure X causes Z causes Y, X causes Y. Z in this case is a mediator. When you control for this mediator, you are estimating, you are blocking this path, but you leave this path open. You can do that, and you will be right if this is exactly what you wanted to estimate. However, if you wanted to estimate the total effect to control for a mediator, it's a very bad idea. Now, a more worrisome case is this one. Z is a confounder because it impacts Z, it affects Y, and then X causes Y. When you leave this uncontrolled, then there will be a bias estimation of beta. Let's look at the mystery of time-varying risk premia. And this is something that has puzzled authors for decades, really. Why is it that factors sometimes work, sometimes do not work? The answer is when you have a confounder that is not controlled for, it could be that gamma changes, and you are estimating a beta that will be very heavily biased. So the answer to the mystery of why there is risk premia that changes over time, why it's so unstable, is because researchers do not control for confounders. Now, let's think about type B2 spuriosity. That's the one that occurs for the opposite situation when you over-control. When you over-control, in this case, for instance, you're controlling for a mediator, in which case you are missing the total effect, or in this case, when you control for a collider. When you control for a collider, now you are opening this backdoor path, and beta will be biased. So this is a situation that is also very worrisome, because sometimes you fail because you didn't control, sometimes you fail because you control. You need to declare the causal graph. Whenever you read a paper in the factor investing literature, or in econometrics in general, and someone proposes a specification, and there is no causal graph associated with that specification, most likely that specification is wrong. And as a result, there will be false positives and false negatives. So this is what is called Bergson's fallacy, when you control for a collider. Let's look at type B3 spuriosity. This is the result of a specification searching. When you look at standard econometrics textbooks, typically what they recommend is that you run a number of regressions, and then you pick the best one in terms of explanatory power, in terms of greater R square, and so on. Well, when you do that, not only you are engaging in multiple testing, which would be the case of false positives that results from not controlling for growth in the false positive rate, but in addition, what happens is that now you are not making a decision on the specification based on a causal graph. You're deciding your specification based on associational estimates, essentially based on correlation. You are deciding your specification based on association, not on a causal statement. So that will, of course, lead to a number of false claims, too. Let me illustrate these examples with these cases, type B1, B2, and B3 spuriosity with Monte Carlo experiments. So the first structure is what is called a fork. A fork occurs when, well, you have a fork. Z is impacting X, is impacting Y. You run this regression, right? You run a regression where you don't control for Z, it's just the intercept and X, and you get here an R square, 25%, and you get a p-value of 0, essentially, because the t-value is 40 plus. So many researchers will stop here and say, OK, there is an association between X and Y. Well, of course it's not. There is none. This is a Monte Carlo experiment. I have chosen the data generating process. I know for a fact that there is no effect between X and Y. Why is the regression telling us that there is an association between X and Y? Well, because the backdoor path is open. The solution is to control for Z, and then we will get an R squared that is better, around 50%, and we will see that the p-value for Z is essentially 0, and the p-value for X is very high. So you could tell me, well, Marcos, that proves the point that doing this specification searching is a good idea, because eventually you will find a confounder, introduce it in your model, and you will obtain an unbiased estimate. Well, here we got lucky, but what when we use a different structure, what is called an immorality? Whoever came up with these names, but you know, this is the case where X impacts Z, Y impacts Z, but these two, there is no arrow between the two. OK, you run your regression, and what you obtain is a p-value of 0 for X, of 0 for Z, which is a collider, but now we have introduced it as a control, and now you have an R square of 50%. Now the researcher might be very happy, because in fact, when we remove Z, the R square drops to essentially 0. So if you are using a specification searching algorithm, now you will obtain a false result. This is false. And look, this is a very simple structure. Of course, there are colliders all over the place in the economy. The moment that you introduce in your regression, the result is completely biased. Now, let's look at the third case, a chain. This is a more interesting structure, a little bit more complex, but very common in investing, in finance. This is a case where Z is both a mediator, but is also a collider. You can see it here, right? A collider, but also a mediator. What do we do? What do we do in this case? Well, now, when you run the regression with this structure, so you want to control for X and Z, you are controlling for this collider, which opens the backdoor path, and now there will be an association, but the association that you are measuring is not 2 or 1 and 2. It is 1, 3, 4, 5, is 1, 3, 4, is the backdoor path. That's what this regression is giving you. It's giving you something statistically significant, R square of essentially 80%, p-values essentially 0. A researcher will be extremely happy about this. We'll write the paper, type it, and send it to the Journal of Finance. Wrong. These estimates are completely biased. Now, when we do not control for Z, now we have this path is blocked because this collider blocks 1, 3, 4. What remains open is 1, 2, which is what we wanted. And now there is a change in the sign of X. Here it is 1, here is minus 0.5. So not only the model that gives you the highest R square is the one that gives you wrong estimates, it's giving you even the wrong sign. You will do the opposite of what makes money. You will systematically lose money because you will buy things that you should have sold. You will sell things that you should have bought. Now, the R square of the correct model is only 15%. It's not 80%, it's only 15%, which means that using a standard econometric procedures, the researcher will lead us to a model that loses money systematically. And look, this is a very simple structure. Causal structures in finance are way more complicated. I could put here a model, a causal graph with 20 variables, with all sorts of connections, and unless you have a causal graph, you have no idea what the specification of the regression model should be. Now, think about this. We have hundreds of thousands of professors publishing papers that they need in order to get tenure, which of course they should. They need to publish, they need to make discoveries. But none of these papers, essentially none of these papers, propose a causal graph. So whenever they confront something like this, they will go for whatever gets them published. And then some investment firm will take this paper, package it into a product, and it goes into your 401k. So what do we do? This is an amazing plot. This is the plot of the performance of all ETFs, all of them. All ETFs, factor ETFs, and this is the performance of the backtest, essentially the performance that went into the paper. This is from the moment that the firm took the paper and filed it with the SEC to apply for permission to market this. Performance is already flat, and this is the day that the fund begins to be marketed. You can now trade it. And you can see that it is not that the performance is ascending until here and then it flattens, in which case you could say, well, you know, maybe the opportunity is not big enough, so all the alpha has been arbitraged away. No, no. The performance flattens the moment that the application for the permission, essentially the moment that the model has been fixed. The moment that the model has been fixed, therefore, all of this is out of sample performance. This points to backtest overfitting. There is massive backtest overfitting taking place. Now, when you look at the most important papers in the literature, these are the Nobel Prize winning papers, like Fama and French, etc. These papers were written at the moment that, to be fair, these tools were not well developed. Perhaps they were known by some researchers, statisticians, but they were not well understood in our community. So, to be fair, they did what was common practice at the time. Now, of course, we know better. What is it that we need to do? Well, we need to identify what are the causal graphs involved in a regression before we choose the specification. Once we know what we are controlling for, of course, the causal graph can be wrong, but at least our statement, our assumptions are transparent to everybody. And now people can challenge our causal graph, modify it, introduce their own assumptions, and run their model based on their priors. But that's not what is happening. Essentially, what people are doing is they engage in massive p-hacking. They run millions of regressions. Number two, they under control. Even in Fama and French 93 and in Carhart, they mention several variables that do not make it into the regression. Right? So they perhaps, Fama and French 93, they miss confounders, they mention momentum, they mention macro variables, and they don't put it in the model. No explanation as to why. In theory, it would be because they believe there are colliders, but nowhere it says that. Then we have the problem of over-controlling, as I said, which is even more worrisome, I would say, because there are plenty of colliders in finance. And then specification searching. So these are essentially the four cardinal sins, right? You have p-hacking, you have over-controlling, under-controlling, and specification searching. This is what is the reason, the cause behind this underperformance that we observe in the first slide. So, based on this, what I propose is that we establish a hierarchy of evidence in finance. Not all empirical studies are born equal. The reality is that sometimes the evidence is very strong, sometimes is very weak. It's anecdotal at best. On one hand, you have expert opinion. You know, some investment guru tells you, "Oh, I see in the future that this is going to happen." Well, look, this is not a very sophisticated statement because everybody will have their own visions, right? This is anecdotal evidence. Then you have case studies. So, for instance, a broker report, an analysis from a bank that says, based on our understanding of how banking works, we believe that, I don't know, UBS is underbought and you should put in your portfolio. It's not really an empirical analysis. It's more of looking at some evidence, anecdotal evidence, and making a statement. I don't say that they don't have value. I'm just saying that they do not have scientific value, which is very different. Then you have econometric observational studies. So this is really the most important part of the financial literature. This is the factor zoo. It's definitely better than case studies. These people really, they actually run some statistics through their models, not the best statistics, perhaps not in the purest way, but there is definitely some care is taken into finding these correlations. It's still low rigor. Essentially, what they are telling us is there is a correlation here. We don't know why, but you should invest in it. Wrong, right? There is a correlation here. It's something that deserves additional scrutiny. It's not something that you should invest in just because there is a correlation. Many people tell me, well, but as long as I'm able to predict things, why shouldn't I invest? Let's say that I don't understand why X and Y are correlated, but I know that X occurs before Y. I have observed X. Why shouldn't I invest in the outcome Y? I don't know what is the mechanism, but there is a very strong correlation. Isn't that enough? And the answer is, of course it's not enough. Because you don't know what is the lurking variable that is going to flip the switch and make the positive betas negatives, and therefore you're going to lose money non-stop. It's not enough to rely on strong correlations. You need to, at the very least, rely on simulated interventions. A simulated intervention is a study that relies on a causal graph that is hypothesized. Perhaps it has been discovered utilizing various algorithms, like PC algorithm. The causal graph is hypothesized, and is presented as an unproven claim. So the author is telling you, if you believe that this causal graph is correct, this is the right way of structuring your regression. And these are the right controls, these are the right estimates. Now, you may disagree with the causal graph, and that's fair, because two reasonable people may disagree on the assumptions and still understand, given these assumptions, which you may share or not, definitely the empirical analysis was done correctly. And that's a simulated intervention. In many cases, that's the best we can do in finance, but this is definitely much better than hiding a number of choices, causal choices in your regression, and then portraying a result as something that is going to generate profits. A little bit better is a natural experiment. In a natural experiment, what you do is you take advantage of nature randomizing some assignments of subjects to various groups, a control group and the group on which there is a treatment. And then you observe what is the effect. This can be done very often in finance because, as a matter of fact, randomicity is all around us. The moment that a number is released, the moment that there is an intervention by the government, the moment that there is a corporate action. So there are some random effects, some effects that occur at the random time that allow you to conduct some natural experiments. And then, of course, the best that you can hope for is a randomized control trial. This, in fact, not uncommon in finance. Banks do it all the time. They produce what is called algo wheels. An algo wheel is a kind of A/B testing where you receive an order, you randomize it, and depending on the number that comes out of the random generator, you're going to send it through one algorithm or another algorithm, and you're going to observe the difference. And these are, of course, a very successful method that is used routinely by the industry, not really by academia. So, in short, there is a hierarchy of evidence, and we need to be very aware whenever we hear a claim, whenever a financial product is offered to us, whenever a paper is published in a journal, that even if the journal is very reputable, let's say the Journal of Finance, it could be very well low rigor statement. And perhaps the claim appears in a journal that is not very famous, that doesn't get you tenure, but it could be very, very rigorous. And I could give you endless examples of such papers that may end up in it could be a randomized control trial that ends up in not a very popular journal, perhaps a journal of trading or some journal of market microstructure. On the other hand, you will have many papers that end up in the top journals, and really what they have done is they have reported some correlations and make the statement that you should invest just based on the correlation. Let me finalize with an invitation. At Adia Lab, we have offered an award, $100,000, to the best paper in causal inference applied to investing. What we would like is to incentivize that researchers do things with proper statistical methods. And I hope that all of you will submit. We have already received quite a few papers. The deadline is end of the year. And I think that it could be a moment that is, could be a watershed moment for the industry when researchers finally begin to use the statistical techniques of the 21st century. Thank you very much.
Thank you very much for that. Man, what a very interesting talk. That was taking me back to the first time that I encountered factor investing and like the French framework, probably about 15 years ago. And something always kind of bothered me as I was reading about it back then, but I never really had a language to explain what it was that was irking me. Now I think I have an explanation for it, so thank you for that. Are there any questions?
Great talk. Thank you very much. Are you aware of any reputable is maybe not the right word, but investment and management firms other than your own that are rigorously and carefully exercising this sort of discipline in actually managing real money?
I am. In fact, as it relates to execution, many firms utilize proper causal techniques. They may call it A/B testing, but for some very specific uses, they do it. They do it right. Now, for other cases, there is really very little incentive. Why? Because a portfolio manager receives a free call option to invest some assets. So there is a competition between portfolio managers to receive funds, and they tend to inflate results in order to receive allocations. So the industry is set up in a way that, in fact, disincentivizes the use of proper statistical techniques. That is not the case at institutions that are not structured in a performance fee model. For instance, sovereign wealth funds. We are expected to deliver performance for a country over the long term. So it's not about achieving a particular number this year. It needs to be over long periods of time. So the structure of these organizations does not really incentivize inflating results. You want to have the right results because you need to deliver this performance over long periods of time. But you're making the right point, and it's, in fact, the industry does not encourage the use of proper statistical techniques, hence the initiative of declaring this award. Yes?
Thanks for the talk. So I come from the world of biology where there's like more constrained laws of physics. Whereas like in the field of finance, you have like a positivity evaluation every single day. Mm-hmm. Because like market behavior is not constrained as much as human biology. Yep. And it will move faster. Yep. So how do you recognize when you're in a zero evidence positivity evaluation environment versus when you're not?
Yes, so that's a great question. Finance differs from biology and other experimental sciences in a number of ways. Number one, we cannot conduct experiments, control experiments in many cases. That's why we need to simulate interventions. That's why we need to apply natural experiments. So that's reason number one. Number two, our variables are typically fail tests of invariance. So they are non-stationary variables. There are changes in regulations. There are interventions by governments. Also, there is a very strict competition. That's number three. Very strict competition between market participants that it always brings the alpha down. Because in order to make $1, someone has to lose $1. And as a result, if someone constantly loses $1, eventually that person will disappear and the opportunity disappears. So it's a very competitive world where opportunities typically do not last very long. As a result, what is it that we can do? Well, what we can do is we can at least state our claims correctly. We need to state our assumptions, and then let people challenge those assumptions. Perhaps these variables are going to experience a structural break as predetermined by the causal graph. Let me give you an example. The flash crash of May 6, 2010. So around noon, the S&P is down around 4%. It has been drifting very, very slowly. Market makers are struggling because they see a very highly correlated, negatively imbalanced order flow. So they're struggling, but they're still in the market. Eventually, the market runs out of market makers, and the price plunges within a couple of seconds, something like 6%, and then it begins to bounce back up. Now, many market makers went out of business that day because they developed models based on associations. This had never happened before. Therefore, models that based on associations, they are always backward looking. This association was not observed before. Therefore, they remained in the market providing liquidity until eventually they went bankrupt. However, market makers that rely on market microstructural models knew that they needed to monitor for negative order flow, toxic order flow. This is the order flow where you provide liquidity at your cost. You are being adversely selected. Those market makers that relied on a causal theory made a ton of money that day. Why? Because they knew that they had to get out of the market. You see, the theory predicted something that had never happened before. That's what good theories do, right? That's what the theory of relativity did. It predicted that if you wait for this solar eclipse, you're going to see how the sunlight is curved by the sun. It had never been observed before, but Einstein made this risky forecast, this risky proposition. And the fact that he predicted something that had never been observed before gave a lot of credibility to his theory. And today, we have performed extensive testing of the theory of relativity, and so far it's holding up. Will we ever find? Of course, we will find one moment where there is some phenomenon that the theory of relativity cannot solve, but it is pretty good so far. The same happens with finance. Our theories do not need to be perfect. They need to be complex enough to take into account potential black swans, so that when the black swan occurs, we don't get caught like on May 6, 2010.
Thank you very much for the talk, Marcos. You're also
right.
getting praise from the live stream, and a couple of questions. So first one is, what do you think of causal graphs in light of what Soros called reflexivity? That is the circular cause-effect relationship in financial markets. Thank you.
Sorry, what is the question?
What do you think of causal graphs in light of what Soros called reflexivity, being the cause-effect circular relationship in financial markets?
What Soros called reflexivity?
Yes.
Reflexivity.
Reflexivity.
Okay. Well, I don't think it's a causal theory. Look, in science, there are situations where a statement is made, and we call these statements laws, which of course sound very strong, right? The law of gravity, or Ohm's law. It sounds even stronger than a theory, right? When you are put between a law, which sounds almost like a commandment, versus a theory, which sounds something weak. But in science, it's the opposite. We give much more importance to a theory than to a law. Why? Because a law is an anomaly for which there is no explanation. When you think about it, Newton never explained why gravity existed. He just made the claim, well, you can measure the force of attraction between two bodies based on the product of their masses divided by the square of the distance. But that's not a theory. That's an observation, right? That's an association that he has made. The same with Ohm's law. These are associational statements. We call them laws because they work. They work always, but we don't really know why. It took 100 years until Ohm's law was explained by a proper atomic theory, and it took about 300 years, I guess, maybe a bit less, 250 years, until Einstein was able to explain why Newton's law, which was not perfect in some cases, it seemed to work. So reflexivity is, in my view, a law. It's not a theory, right? It's an observation that a very successful investor has made. And as such, what it should attract is scrutiny. Why does this thing occur? We need to understand why, but we should not stop at thinking, well, this seems to work, because guess what? Financial systems are much more dynamic than biological systems. Very quickly, things can turn the other way around. In order to prevent black swans, you need theories. Laws are not enough to prevent black swans.
Great, and perhaps one more question from online?
Yeah, thank you very much for that answer as well. The live stream asks, what are your thoughts about effect heterogeneity and external validation in the context of financial experiments? And are you aware of cases of combining observational and experimental data in the field?
Absolutely, absolutely. One of the best uses of simulated interventions that you can think of is you begin with some observations. Based on those observations, you derive a set of causal graphs that are compatible with that observation, right? The observations, because they are associational statements, they can never lead you to a very precise causal graph. Causal graphs incorporate non-statistical data, right? That's why causation is not equal to association. You need to have a framework, a theoretical framework that explains why this association occurs. So you need to work backwards. You begin with the observations. Given these observations, these are the potential causal graphs, and there could be hundreds. And now what you need to do is you need to start to challenge those causal graphs. You say, if causal graph number 1 is true, then I should observe this association when I control for that. You do it, you do that simulated observation, and half of the graphs fail. Okay, so now instead of 100, now we have 50. Now you design a different simulated observation, and by elimination, you end up with a smaller number of graphs. And then what you need to do is you again need to use non-statistical information to make a claim. We do know something about finance and economy. After all, this is not coming from Mars. This is based on human institutions. We have some ideas to why the markets operate in a particular way. So that means that we can narrow down the graphs that are compatible not only with the observations, but also with our understanding of the economy. I'm not saying that there is a particular rule book that you need to follow. I'm not saying that utilizing causal inference, everything will happen automatically. No, but at least it allows us to narrow down what are the possibilities, and very important, state all of our assumptions for everybody to criticize. So again, yes, there are many ways in which you can utilize, combine observational studies with simulated observations to derive causal graphs that are compatible with the evidence, and then that's the best understanding that we have as to how the financial system works. Thank you very much.
Great. Thank you very much. Another round of applause.
Great. Thank you so much.